It's To the Best of Our Knowledge. I'm Anne Strainchamps, and today we have 3 words for you. Science is cool.
My very earliest memories are of being in my father's laboratory.
Biologist Hope Jahren.
He taught at a community college, and in the evenings he would get things ready for the next day. He would maintain the equipment and set up the demonstrations, and I would go with him, my brothers and I, and we would help. I just loved the place. I loved the way it smelled. I loved the bright lights and all the different blinking objects. And from very early on, I thought, when I grow up, I'm going to have a lab, and it's going to have 1 of those and 2 of those, and I'm going to do experiments with my friends. And I imagined that for myself before I even knew what having a job was.
Hope Jahren grew up, and she did get that lab of her own. More than 1. She's had geobiology labs in Georgia, Maryland, Hawaii, and now Oslo. And she thinks there should be more people like her.
I think there's a lot of folks that haven't considered science that would be good at it and would like it.
The problem is, Hope says, most of us don't actually have a chance to see inside science labs. We don't know what scientists do all day, and we don't know how they think. So she wrote a book to try to explain. It's called Lab Girl. It won the National Book Critics Circle Award, and it begins with her own first encounters in her dad's lab.
Well, he had the physics demonstrations. I remember those really well. You know, the balls that roll down a slope and slopes of different shape and, magnets, turning magnets in an electrical field. And, he had laser that you could...
He had a laser?
Yeah. And you could turn it on and clap erasers in front of it. I remember you could fill the air with chalk dust and you could see the beam of the laser, and you could refract the light and things like that. And I remember we'd say, yeah, can we take out this? Can we take out that? Can we do the magnets? And he would never, ever, ever say no.
Now, you've also written really eloquently about feeling that science isn't something that just happens in a lab. Science is practiced in the home, too. It's maybe the place where most of us learn something about science first. Looking back, what do you feel like you learned about science from your mother?
My mother thought about things while she did them, and she was constantly optimizing her activities in terms of either the resources she was using or the time that it took to do it or the amount of labor that it took to do it. You know, when you make jam, how few dishes can you dirty during the whole process, from picking to cleaning to boiling to canning? How few times can you heat up the stove? And I saw her do that with cooking, with sewing, with gardening. Think about it while you do it, before, during, and after you do it, and tweak the way you do it. I was just taught that was how you lived life.
You wrote somewhere that I remember, because that so struck me, that she knew how to adjust the tension when she was sewing on buttons.
Oh, absolutely. So if you replace the buttons on a shirt, you do the cuffs differently than you do the top one, differently than you do the bottom one, because you're always buttoning and unbuttoning, the cuffs or the top. So you would use maybe different thread, you would give a different tension to it, you would knot it differently, etc. But you would work that into whatever you were doing. How were these different objects going to be used in the long term? And try to think 1, 2, 3 steps ahead with everything you did.
You wrote this fabulous blog post I wanted to ask you about. I think it was a piece you were writing about why you love science, but I do remember that this post began with the line, "My grandmother knew how to cook an owl."
Yes.
Really?
Well, these were hard days. The Depression hit the Midwest pretty hard. So the combination of having a lot of mouths to feed and having the woods at your back door brought some strange things to your cooking pot, whatever you could catch. And so I knew that the women in my family could do that if they had to. And I knew that as a woman, as my mother's daughter, there were problems that could be solved if they had to be solved.
Well, I'm wondering if part of the reason you became a a professional, paid, tenured scientist with a lab of your own. I wondered if any of that is because of the women in your family, like your grandmother, like your mother, women who didn't have the opportunity to train as scientists, but who might have liked it.
Oh, absolutely. I mean, I'm always very, very sensitive every day, every hour to what a good fortune it is to be able to think for a living. Women's lives didn't have room, for professional science in the way that I practice it now. And yet, they used all those skills, planning and calculating and guessing and trial and error and working. That's something we've been doing for generations and generations.
Why did you choose plants? I mean, you liked science first, but you could have gone into physics or chemistry or lots of other things. So why plants?
I chose plants because it was really the hardest problem I could think of. I was looking at the chemistry of a material that is found inside a seed. So it's a tree called the hackberry tree, and inside the hackberry fruit is a pit that surrounds the endosperm, the part that will grow into another tree. And this material it's like a peach pit. It's hard because it's actually made of rock. And we were interested in the process of how that rock forms. And we had some experiments set up. I was a graduate student. These were some trees in Colorado. We had it all staked out. We were looking at the water coming into the plant and the weather, and the grand finale was going to be when they bore fruit. And by the end of the year, none of the trees at or near my site blossomed or bore fruit. They just didn't. And it became very, very clear to me that these things were alive. They were not going to make fruit so that I could have a nice thesis. They were making fruit and making seeds in order to do something that was part of their agenda. And it sounds simple, but to have that really driven home that you're dealing with a living organism that's just as alive as you are. I think we know plants are alive, but I think the idea that they are as alive as we are, they're just doing different things using different strategies for different reasons. And I thought, wow, that's a mystery I could spend my whole life on.
What I love about that also is that glimpse of a world in which all this green stuff around us isn't just passively alive, it's actively alive, making decisions, doing things, because that isn't how we think of plants. We think of them as, green backdrops.
Right. So, and I try to talk to my classes about generalities, boiling it down and saying every living thing, whether it's a worm or you or me or a tree or a microbe, has 5 things they want to accomplish in order to keep their species going. And that's to grow, to store resources against hard times, to maintain their tissues, to heal, to defend themselves against whatever threatens them, and to reproduce eventually. And if we look at any living organism, we see those 5 activities. And if we look at plants, we see them doing it with a totally different suite of tools and a different suite of responses and a different suite of priorities. And that's what I think is really fascinating.
Do you feel like you've learned anything that has then suggested strategies to you, either for things, ways to flourish in the world, or else just ways to see the world differently?
One thing I've been thinking about for many, many years, and it comes from a brilliant professor I had very early on who said to me very simply that the difference between a plant and an animal is that if you don't like it where you are and you're a plant, you can't get up and walk away. And ever since then, I've been thinking about, as animals, that is so much our strategy. If it gets cold, we go indoors. If we move and we attack something or we flee from it, so much of how we deal with the world is through movement. And plants stay. They stay there and take it. The tree outside, gets cold, it gets hot, it never goes indoors. It doesn't run away from all the things trying to eat it. And what do you learn from life? How do you interact with the world differently if you stay? And that I think about more and more because I have moved around so many different places, building labs and trying to make ends meet. And I'm starting to look at life and say, what do people get from staying? How do we grow in ways that we don't grow if we're putting all that energy into running around?
Hope Jahren is a geobiologist at the University of Oslo. Her memoir is called Lab Girl. When I think science lab, the first thing that comes to mind for me is a microscope. There are so many kinds. Electron microscopes, dark field microscopes, X-ray microscopes, atomic force microscopes. But for sheer coolness, give it up for the 50-cent microscope, designed by Manu Prakash.
It's essentially a sheet of paper, and one of the things that you do is you don't just get a microscope, you fold it yourself. So
Manu is a bioengineer at Stanford, and he's invented a paper kit that unfolds into an actual working microscope. And Steve Paulson is getting a lesson in putting it together.
And this is popping out some of the parts.
This is like what kindergartners get in school.
Yeah. And I think philosophically, it's actually very important to think about that because it's an object that's not foreign to us.
The thing about Manu's paper microscope is it's really little, like smaller than a cell phone. And that's the point. He wants the tools of science to be portable and inexpensive, so they can go anywhere in the world, be used by research labs and classrooms. And this 50-cent microscope can actually detect malaria and lots of other infectious diseases.
So, Manu, you have brought in not just the paper microscope, but you've put all kinds of stuff on the table. What else do you have here?
Yeah, I mean, this is another tool that we made a couple of years ago. It's a music box, so I'm going to play it. This is a gift that my wife gave me on a Christmas. She stole it on a white elephant. And it occurred to me, music notes are very precise. That's why we enjoy music. And we could use...
Manu realized he could create a similar tool, he says something like a punch card tape, to dispense very precise amounts of chemicals for diagnostic tests. And this is just one of the many gadgets he's invented in his lab to help us see a world that was once invisible.
Before coming here, I had found a flower, and I just sprinkled something on top of the flower. You see these little blotches?
Yep.
And any normal glass slide fits in. And right there, you're going to see beautiful footballs. Many, many, many of them. They're yellow.
Oh, yeah. Huh.
And what you're looking at is essentially pollen grains that are magnified 450 times.
The slide that you're putting in is the same kind of slide that everyone who uses a microscope uses, just that you have your little folding microscope.
Yeah,
something made out of paper.
Yes, and something that you carry in your pocket. And that access becomes very important. Just like pencils are everywhere, so should be microscopes.
So it's made of paper, but it seems pretty durable. I mean, it doesn't look like it's just going to rip or crumple up.
Yeah, I mean, that one I've had for 2 years. This is waterproof paper. We worked for many number of years. We throw them from third-story buildings. We take them out in field trips out in the middle of nowhere, using them to diagnose diseases. So robustness and portability are key. And then effectively, they are so cheap in bill of materials that you shouldn't be scared of breaking a scientific tool. You know, any scientist can tell if you really care about making discoveries, you need to break some china in the lab. You got to get in there. You got to try new things. You can't be afraid of your tool.
Now, I've heard that research labs around the world are using your little paper microscope.
We made 50,000 of them in the lab at Stanford, and we posted a note saying anybody who wants one can get one. We got swamped by requests from around the world. So we've shipped 50,000 of these tools to 130 countries. And the tool is exciting, but the most gratifying feeling is when a kid in Namibia pulls out something and makes an observation and shares that with the world through your tool. That's very powerful. And, that's the experience that I live for.
So how did you come up with the idea for this? Did you want to invent a new, very portable, very cheap kind of microscope, and then you wanted to figure out how?
I am a kid at heart. I make tools for myself, and then they're useful for others. That's great. I grew up in India, so I understand the value of not having something. And I grew up in a small town called Rampur. I didn't have access to microscopes or fancy labs or even understanding what science deeply is. And we need to think very hard about access and equality. We need to democratize science if we're going to engage society deeply in science and not have be people just experiencing science through reading their Facebook posts or reading books. I mean, that's knowledge transfer, but experience of science is very expensive. And so the driving force for this tool was, how do you bring that experience to be both fun, enjoyable, and at that same time accessible to all?
So you want both to be educational so that students in schools can use it, but you also want it to be used in research labs.
Absolutely, absolutely. We made this observation that the types of tools that you need in the scientific fields, that when you're using them out in tough field conditions, portability and low cost are the same things that you need for kids around the world. So they're almost exactly the same sets of tools. So it's not just about, you're a kid, you should use this tool. This is a tool that I use every day.
Really? So what kinds of actual health problems might this microscope be useful for?
So that's very interesting because that's really where we started as a question. This idea that diseases are caused, or many diseases are caused by microbes that you can't see, the classical germ theory. You go out into many places and many people, because they haven't experienced the microscopic world, don't even believe in germ theory. Schistosomiasis is one that we demonstrated in Ghana and Kenya for school kids to be able to use the same microscope to teach them biology, but use the same microscope to diagnose their own diseases. We're developing a new tool for malaria. That's been our biggest effort for the last couple of years. We just tested that prototype out in Madagascar.
So how would this be used for malaria?
So one of the things you would do is you would take a finger prick, which is a common standard practice that's done. You take a drop of blood and you would smear it on a glass slide. There is a dye that's commonly available. You dip that for 30 seconds to a minute. You slide that in and then you search for the parasites. Parasites have faces. You can identify them when you get face-to-face with them. And that's one of the criterias for being able to do perfect diagnosis.
Wow, so you could kind of get an instant diagnosis of whether someone has malaria.
Yeah, and then also there is ideas about how to train healthcare workers around the world such that microscopy becomes a second language to them. I mean, how do you expect people to know microscopy if they don't have a microscope?
So put this in some perspective for me. I'm assuming that in a lot of countries, especially those that are struggling with malaria, there's not a whole lot of money around to do a diagnosis of malaria, for instance. How might this change the way healthcare is conducted?
Malaria is one, but there are hundreds of infectious diseases. If you just look at malaria alone, we need to do of the order of 1 billion or 2 billion tests per year on people around the world, and that's not happening.
On the surface, it seems, this is all so low tech.
Mm-hmm.
I'm guessing it's actually not that low tech. I'm guessing there's a lot of science and engineering that's gone into building these tiny little devices.
Yeah, I think this is something that's really valuable in terms of thinking about how our perception of an object changes with how we associate that with complexity of technology.
This is totally fascinating, I have to say. Seeing, this, whole jumble of what look like little toys in a way, but that you make inventions out of.
Yeah, and I think one value that comes out of it is when somebody looks at this object, I've had these conversations with kids, there's a very strong belief that, I can do that too. And that's that's a meta conversation to be had, is how do we demystify scientific tools? That's why the Foldscope doesn't come as an assembled kit. You have to build it, because when it's not working optimally, it's your job to fix that back again and even improve it further. So that process is at the core of science. Many tool makers in the history of science have used their tools to make discoveries. it only happened because the scientist was so one with their tool that they understood an anomaly.
You know what I find interesting about what you're saying is that I might have thought you would say, oh, malaria is this global health problem.
Yeah.
What can we do to fight malaria? I'm going to go build a microscope. Because that's not the way you think.
No, I want to not just solve malaria, but every possible problem. And that has to happen from ground up, getting a much larger group of people engaged in science. Because one of the things that ends up happening is in the current society, even when a tool arrives, it doesn't get used properly. It just sits there and we forget about it. So the bigger picture is how do you get majority of people in society to not just accept science, but engage in science? When that happens, we don't have to worry about malaria. We don't have to worry about mosquitoes. We're going to find a profound change in how problems are solved. I very strongly believe that people are the most important resource that we need to invest in.
This is incredibly inspiring. Thank you.
Thank you so much for having me.
Manu Prakash is a bioengineer at Stanford and the inventor of the 50-cent microscope. He was talking with Steve Paulson. Coming up, astrophysicist Neil deGrasse Tyson takes us on an unbelievably cool science adventure. He's going to, wait for it, hard boil an egg. I'm Anne Strange-Shams, and this is To the Best of Our Knowledge from Wisconsin Public Radio and PRX. Okay, the moment you've been waiting for. Neil deGrasse Tyson, head of the Hayden Planetarium, holder of Stephen Hawking, Hubble, and NASA awards, and People magazine's sexiest astrophysicist alive, is going to hard-boil an egg.
Science is about measurement. There is no maturity of a scientific field until they have come up with a system of measurement. If you've ever boiled eggs to make hard-boiled eggs, and you notice that the outer edge of the yolk, the edge that's between the yolk and the white, have you noticed for some eggs it's brown and others it's not? Well, there's a reason for that. I learned from my wife, who has a PhD in mathematical physics and thought about this and made the measurements. So that turns brown if the egg stays hot for longer than necessary after it has become hard-boiled. So what you should do is, after the eggs are hard-boiled, immediately run cold water on them. And leave it in cold water until they no longer feel hot to the touch. And then the outer edge of the yolk will stay the same color as the inside of the yolk. People wondering, oh, how soon will the water boil? I will take out a thermometer and I'll measure the temperature. It's 180 degrees and it's been heated for 20 minutes. I can make a judgment as to when it will be boiling. So scientists would have never come up with the expression, oh, a watch pot never boils. Measure the damn thing, okay? So that you will know. Little things like that, but it means you had to do the experiment. You had to be curious about it. Don't just take the world as handed to you. Question it. Experiment with it. That's the fun part. The day you've lost your curiosity is the day that the world is handed to you and you no longer interact with it. Other things, the Bengals were playing, I forgot who the other team were, Cincinnati Bengals during the football season, and they kicked a 50-yard field goal, a long field goal. It hit the left upright and careened in for the win in overtime. And I said, wait a minute, what's the orientation of that stadium? Did a quick calculation and ran the numbers, and I said, oh. Then I tweeted that the winning field goal of the Cincinnati Bengals was aided by a 1/3 of an inch deflection to the right from the rotation of the Earth. So that's how differently the world looks to a scientist. And this is just science literacy, by the way. I don't think you have to be a scientist to think this way. You just have to be curious. And what is a scientist? It's a kid who formalized their sense of curiosity in the world. That's really all that's going on there.
Astrophysicist Neil deGrasse Tyson. There's a mental state that elite athletes know well. When everything clicks and time disappears, when you're in the zone. Scientists call these flow states. Here's writer Jamie Wheal.
The funny thing is about those experiences is that for most of us, they happen accidentally, they happen occasionally. They might have happened a lot when we were children or a lot when we were athletes playing team sports. But as our lives change and get more complicated, they either just diminish in our lives or we just kind of fly blind looking for them, sort of nearest the last place we found one.
Jamie Wheal is an expert on peak performance. He's helped everyone from Navy SEALs to NFL, NBA, and Major League athletes achieve flow states. And he says neuroscientists have finally figured out how to hack the brain so any of us can do it.
We can do a literal end run around our waking conscious selves. You don't have to use your waking conscious self to try and get rid of it. It doesn't work. It's like trying to hide your own Easter eggs, But what you can do is you can say, hey, I'm going to calibrate my breathing, my brainwaves, my heart rate, my posture, and a host of other neurophysiological factors. And that's what we're saying is game-changing.
So the psychologist who, as far as I know, first began writing about flow is Mihai Csikszentmihalyi. And since then, it's been studied a lot. What would surprise people to know about it today?
That's a great question. I think one of the things that's exciting is that it's no longer just a psychological study. So when Csikszentmihalyi first started, there wasn't real-time brain scanning. There wasn't the ability to check neurotransmitters in a system. There wasn't the ability to see what was happening under the hood. So all he really had to go on was psychological, subjective self-reporting. And they literally had little pagers buzzing in people's pockets. So someone would maybe be in a flow state where they were losing track of themselves. And then bzzz, the little text thing would be like, on a scale of 1 to 5, how flowy do you feel right now? Which obviously kind of defeats the point. You're like, well, I was there. Now I'm not. Thanks. Now how do I get back?
Can you actually break this flow state down in terms of specific biochemicals, neurochemicals that need to come online?
Sure. Yeah. We can first start with what it isn't. And what it isn't is 21st century normal, that tired, wired, stressed experience. And what that looks like as far as the neurobiology, we're talking right now, anybody listening, we're probably in a beta brainwave state. That's a relatively fast brainwave state. It is particularly, it's correlated with activity in the prefrontal cortex, which is the front part, the complex part of our brain that houses most of our sense of self, our sense of executive function, delayed gratification, long-term decision-making, abstract planning, all that kind of stuff. So that stuff's up and running at full speed, humming along with beta waves. And the tired, wired, and stressed part, we're not dodging saber-toothed tigers these days, right? So our stress response, which is a lot of norepinephrine and cortisol, right? Those are super helpful for sudden, sharp fight or flight moments, but they're terrible for us to just have them on 24/7. There we are in traffic, rehashing a conversation we wish we had with our boss. I have phantom phone buzzing in my pocket. Ooh, was that a new update? What was that? Right? Those kind of moments eat us alive. So that's normal. And
that sounds horrible.
Isn't it? You're like, how do we do anything? So then you realize, okay, so ecstasis, these states that take us outside ourselves, that's just the old ancient Greek literal definition of it. That signature shifts in every single way. So our brainwaves tend to slow down from beta to alpha and even theta. And those are much slower, more contemplative, relaxed, almost sometimes even dreamy or hypnagogic states, those kind of states in between waking and sleeping. Our brain activity, the network that basically supports and creates our sense of self-awareness, some of those nodes power down, and as a result, that inner critic and the self-awareness tends to go offline. The stress chemicals get flooded out. So nitric oxide quits a neurotransmitter and it kind of pushes through our system and flushes out those stress chemicals, and in come dopamine, endorphins, and anandamide.
These are all the pleasure chemicals that the body
They sure
can
are.
produce. So is the shorthand version of everything you're saying just do stuff that makes you feel good? Because on the other hand, if I did that, I might just sit around at home with giant cartons of ice cream.
Yeah, well, I would say, in some respects, it's sort of like hashtag do the obvious. Sleep more, move often, eat well, be grateful, get outside. I mean, none of this stuff is mysterious. It's just, do we give ourselves permission in the pell-mell of the day-to-day to actually say, no, this stuff matters?
I know I should do all of those things. We all know we should do all those things. Honestly, pick up a, People magazine or Red Book or something, and they all tell us we should do all of those things, and a lot of us try.
A, this stuff sounds so obvious that we can just kind of forget it and not do it. And B, how would we give ourselves permission to what might otherwise seem self-indulgent? I actually shouldn't be working 70-hour weeks and bragging about them. I should go home after 50, because that's what all the research shows is the massive drop-off in performance. I shouldn't tell myself I'm too busy to have a full breakfast or take a shower standing up. I should take a long hot bath. I shouldn't ignore my primary relationships and my spouse and my children. If I take the time, the performance gains from doing these things are anywhere from 200% to 490%.
So part of what you're prescribing here is common sense, and you make a great point that we know what we should do, we just don't do it. But you should tell the story. There's a story you tell in the book about how Navy SEALs are figuring out how to deliberately induce this flow state in order to get small teams to develop this kind of hive mind.
Yeah.
Tell us what the SEALs are doing.
We were privileged enough to spend some time with DevGru, or what is sort of commonly known as SEAL Team 6, and see how they learn and operate. And beyond all of the heroic physical and tactical things that they train for, the key thing that their commanders are looking for is, can one of their SEALs, with chaotic conditions all around them, which direction does he go? Does he merge with his teammates? And do they create basically a shared real-time decision-making and action collective? Flipping the switch is what their commander called it.
What does that even mean?
The technical term that the SEALs use is dynamic subordination. What it means is, regardless of rank and regardless of whatever they planned before they actually dropped out of the helicopter to go on the mission, whoever knows what to do next is in charge. They take the lead. So they're offloading elements that would have been a rational, separate individual would have to handle all by themselves. And they're trusting each other. And that trust isn't just awarded, it's earned. It's earned every single day.
I guess I'm not entirely sure what you mean. They're not stopping to say, okay, who thinks we should go right and who thinks we should go left?
Well, no, I mean, that stuff's out the window. It's not different than, Steph Curry and the Golden State Warriors, right? We clearly know it when we see it, and we pay dearly to be in the presence of it. And that experience can be as simple as singing in a church choir together. It could be line dancing on a Saturday night, here in Austin at the Broken Spoke, right? It could be any of these moments where we just set aside our fragmented sense of ourselves and we do something greater together. That's usually pretty intoxicating.
Jamie Wheal is the co-author of Stealing Fire, How Silicon Valley, the Navy SEALs, and maverick scientists are revolutionizing the way we live and work. Coming up, Science is Cool heads to the world of primatology with orangutan expert Birute Galdikas.
Did you ever see that movie, Forbidden Planet?
Explore all the wonders of a vanished civilization.
That's one of my, 10 most favorite movies.
What is it, Randall? Sir, radar just picked up something.
There's this invisible monster, and when he walks...
This way, sir, slowly.
The earth trembles, but you can't really see him or her. Well, that's the way it is when an adult male orangutan appears in the trees. You know what it is. You know it's an adult male orangutan. And you know that he's relatively benign.
It's still coming!
You can't really see him clearly, but you can see the trees shaking and the earth kind of moving, and you tremble. I mean, it's involuntary in spite of yourself, even though you know it's just an adult male orangutan. Trees crashing, branches falling, and then he gives forth the long call. The long call is really an awesome sound. almost like a locomotive when a locomotive goes by. I mean, it's so powerful that you can feel the vibrations just go through your body.
Oh, it's stopped now. We'll check over the whole system first thing in the morning.
Aye, sir.
More primates coming up. I'm Anne Strange-Champs, and this is To the Best of Our Knowledge from Wisconsin Public Radio and PRX. You are listening to an earthquake, specifically to the earthquake that caused the Fukushima nuclear meltdown. It hit March 11th, 2011, and was one of the largest earthquakes ever recorded. 9.1 on the Richter scale. Thousands of people died in it. But thanks to this audio recording, thousands more were saved. It's based on a Japanese technology that can detect and record the extremely low-level sound waves of an earthquake 20 seconds before it hits. That's enough time to send out advance warning and save lives. Also up there on the coolness scale is the triad of world-famous field biologists who revolutionized primatology by living in the wild with great apes. They were all women: Jane Goodall with chimpanzees, Diane Fossey with gorillas, and Birute Galdikas with orangutans. Their great ape field studies are arguably some of the most important scientific experiments of the 20th century, and their personal cool factor, to me, is off the charts. Here's Steve Paulson with more.
Today, Jane Goodall is one of the world's most famous scientists. She showed us that chimpanzees, like humans, have very different personalities, and she made several revolutionary discoveries. She found that chimps are tool makers. She observed them hunting other animals, and she also saw them wage war on rival groups of chimps. But what may be the most surprising piece of this story is that when Goodall started her field study in 1960, she had no scientific training.
Didn't have any. None. I was at school. I left school at 18. I got a course of training as a secretary, got a job in London with documentary films, and then decided I had to get to Africa when I was invited by a school friend. So left my job in London, which didn't pay very well, went home, worked as a waitress, saved up my wages and my tips, got a return fare to Africa, and there I met Louis Leakey.
Well, I have to say that is remarkable when you think about it. I mean, back in 1960, you seemed to be the most unlikely candidate to revolutionize our understanding of chimpanzees. Why do you think Louis Leakey picked you to do this field study?
Well, he told me later, afterwards, that he deliberately picked somebody with no scientific university training because he wanted to send somebody into the field with an unbiased mind. And of course, back then in the early 60s, the ethologists of Europe were very reductionist. Humans were the only animals with personalities, minds, and above all, feelings. And of course, I hadn't learned any of that, so I went merrily ahead and gave the chimpanzees names, which wasn't at all appropriate. They should have had numbers, and described those vivid personalities and described many examples of clearly intelligent behavior and emotions that were obviously similar to or sometimes the same as ours.
About 5 years after Jane Goodall went to Africa, Birute Galdikas got the idea that she wanted to study a different great ape, the orangutan, which eventually led to her own meeting with Louis Leakey.
When I was 19, I was sitting in a very large psychology class, and the prof just sort of mentioned the woman living with chimpanzees, and I just knew that this is what I wanted to do. Orangutans had not really been studied in the wild very well, and there was this history of people going out and looking for wild orangutans and not being very successful at finding them. Because of this, over the years, there was this sort of mythology that had arisen in academia, and this mythology basically was that it couldn't be done.
How did you first meet Louis Leakey?
I met him again at a lecture at UCLA, and I just went up to him after the end of the lecture and started talking to him.
And you told him that you were the person that he should send to study orangutans.
Well, I didn't quite say it that forcefully, but I said, I told him that I wanted to study orangutans and asked him for his help.
Well, he had a whole theory of why women would be better field biologists, didn't he?
Oh, he was absolutely convinced of it. He felt that women were much more patient than men. He felt that women would not excite the aggressive tendencies of the great apes as much as men. And he really believed that women were more perceptive than men.
He deliberately chose women. He felt that women made better observers, and he liked working better with women.
Was he right, do you think?
Well, if you look at women in an evolutionary perspective, you find that, and I compare them with chimps, chimp mothers, human mothers, that a mother would need to have been patient, otherwise her children wouldn't do very well, and they don't with chimps. A woman needed to be able to understand the needs of a non-verbal creature, that's our children, before they can speak. And also women traditionally, even if they've been subjugated, have been very quick to recognize the little communication signals in a household so that they can prevent arguments happening before they blow up, keep children out of the way of irritable men.
You know, I think he may be right, at least of women in our society, in that tests repeatedly show that women do see details that men don't see. So I'll give you an example. An experience I had, I was once at the home of an internationally known primatologist who happened to be a man, and I was looking at a picture on his wall, and I said, oh, so these particular primates engage in male-male competition, fight a lot. And he said, what do you mean? I said, well, look, you know, the finger of one of the males is missing. And he looked. And he'd been studying these primates for a year. I mean, there was a picture of them on his wall. He looked at me and he said, funny. He said, I never noticed that before.
That's amazing.
Yeah, he had never noticed that part of the finger of one of his study animals was missing.
Now, these were revolutionary discoveries. For instance, when you saw a chimpanzee using a tool, can you describe that first day that you saw this?
Oh, I can close my eyes, and as I am now, and just see it. I was a bit cold, it had been raining. I was pushing through some tall grass, and suddenly I saw this dark shape hunched over the golden soil of a termite mound, and I peered through the bushes with my binoculars, and the chimp had his back to me, but I saw a hand reach out and pick a piece of grass, and I could see him pushing it down into the termite mound. And the next time, a couple of days later, not only did I see him using the tools, but actually stripping leaves from a twig, therefore making a tool. And that was the exciting thing, because up till then, it was thought that humans and only humans used and made tools, and we were defined as man, the tool maker.
One reason Goodall and Galdikas made so many groundbreaking discoveries was simply the amount of time they spent with the primates they studied. Goodall lived at Gombe in Tanzania for 15 years. Galdikas stayed at her campsite in Borneo for more than 30 years. This was not the way male biologists had typically done their field work.
Basically, it's get in there, get the data, and get out. And I think women have a different attitude. The data is not necessarily everything to them. I mean, I don't want to give the wrong impression that, all male scientists are like this and all female scientists are like that. But basically, I think that we're speaking about different acculturation processes. I've noticed that the male scientist frequently will get the data and it will almost be like a trophy. It'll almost be like a scalp. And Louis Leakey really zeroed in on that difference.
Well, you tell some remarkable stories about one orangutan whose name was, I'm not sure if I'm saying this right, Sugito?
Yeah, Sugito was my first ex-captive, wild-born ex-captive.
Who just clung to you all the time, no matter what you were doing, whether you were taking a bath, whether you were trying to change your clothes, in bed when you were sleeping at night.
That's right. That was exactly what he did. Orangutan infants, like all primate infants, are very needy, and they have to be on the body of their mother.
And he would urinate on you throughout the night?
Yeah, and throughout the day as well. Defecate. I was covered by tropical ulcers. My body was covered with tropical ulcers. It wasn't until years later that I figured out the reason I had all these tropical ulcers was because I was always wet with urine.
You write that your relationship with Sugito became so intense that it really was the most important relationship in your life, with the possible exception of your relationship with your husband.
Oh, that's very true. It was very intense. And in fact, I think this intensity is what caused problems in the relationship with my husband, my then husband.
Mm-hmm. And I would think it would be hard. I mean, here you had this baby clinging to you at night, and your husband is sleeping beside you, and
yeah, he couldn't touch me.
Sugito didn't especially like your former husband.
No, he was just insanely jealous. And, I mean, the relationship was that intense.
There was something else that set both Galdikas and Goodall apart from their male counterparts. Both became mothers during the years they spent in the field, and they raised their children alongside the apes they were studying. Do you think your experience as a mother helped you as a scientist, as you were trying
Definitely, yeah. I understood, like, for example, when a chimpanzee mother is approached by another one and she gets all angry if the child's asleep or something, I felt exactly the same, that these surges of irrational anger if something happens that you think is going to harm or disturb your own child. And so I could much better understand the mother chimpanzees when they behaved in what seemed to be the same way.
And then you had a child of your own, and you were raising him out there at Gombe as you were doing these field studies. I guess it raises the question of whether you learned anything about raising your own son from the chimpanzees you were studying.
Well, I'm quite sure I did. I really looked on Flo as a role model. She was patient and supportive. She was protective, but not overprotective. She could impose discipline when she wanted. She provided a nice, secure base for her kids, and she supported them if they got into difficulties. That's the hallmark of a good human mother.
Well, there was another convention as well in science. I mean, to some degree, it's still there, but I'm sure it was even more prominent back in the early 60s when you were just starting out. And that's that scientists were not supposed to get emotionally involved with the subjects they studied. And it seemed that you kind of violated that rule in your study of chimpanzees.
Well, of course, I didn't know that when I began. I hadn't got any degree of any sort. I'd just done biology in high school. That's why Lewis chose me, he says. You know, I've watched animals all my life, long before I watched chimpanzees. And I think that having empathy with the creature you're watching is an immensely powerful tool. It gives you a platform from which you can start asking questions.
I think when you do field work, you basically not only experience the science and the animal that you study, but you also get to experience yourself. If you don't understand yourself, you can't understand the animal that you're studying and how to study that particular species.
I was sitting in the forest with David Greybeard, and I picked up a fruit and held it out to him. He turned his head away, and I put my hand closer. He turned, looking directly into my eyes. He reached out, took the fruit, dropped it. He really didn't want it. And then he very gently squeezed my hand, which is how chimpanzees reassure each other. And so in that moment, we communicated with a language, or communicated in a way that seems to predate words, perhaps in a way that was used by our own common ancestor millions of years ago. And it was an extraordinary feeling. It was bridging these two worlds.
It felt like interacting with equals. because they were so smart, but yet at the same time, the world of the orangutans rests on such different assumptions about what is important and what isn't. And it's so slow-paced. It's hard to explain, but it was like going into another universe. When I think back about those early days, I tend to forget, how sick I was, and how thin I was, and how weak I was, and how hungry I was. But I remember how happy I was.
That audio is from interviews Steve Paulson did with Jane Goodall and Birute Galdikas. To the Best of Our Knowledge is made each week by a tiny team of audio cool hunters. Charles Monroe Kane, Shannon Henry Kleiber, Angelo Bautista, Mark Rickers, Joe Hartke, Sarah Hopeful, Steve Paulson, and me, Anne Strainchamps. Thanks to all our guests and to you for listening. Be well, and come back often.